So good morning, everyone. My name is Marta Boscariol, and I'm here to present my research conducted under the supervision of Professor Lavinia Tagliabue from the University of Turin and Professor Pieter Pauwels from the Eindhoven University of Technology. So the title of our paper is Addressing Workplace Management Challenges with a System Engineering Approach to Digital Twin Environments. And it investigates how to support large organizations in optimizing the use of their workspaces and assets during a data-driven holistic framework. So according to literature, workplace management has always involved coordination between physical space, assets, and human resources. However, the COVID pandemic accelerated the need for flexibility, hybrid work, and better space utilization. Organizations now face not only operational issues such as asset tracking and occupancy planning, but also strategic challenges like energy efficiency and employee well-being. Traditional systems are often siloed and reactive, making it difficult to adapt to new needs quickly. This work builds on several core concepts, and it aims to tackle the aforementioned issues with a product-centric approach. If digital twins create a virtual replica of physical assets, semantic digital twins add a layer of intelligence and contextual understanding. Knowledge graphs and semantic web technologies enable integration of heterogeneous data and support complex queries across domains. This multi-domain integration is connected with the definition of a digital twin environment. And finally, model-based system engineering provides structured methods to define the system requirements and architecture. These foundations allow to build a scalable system tailored to the complex needs of workplace management. The main objective was to design a workplace asset management system that used system engineering principle and digital twin technologies to support real-time informed decision-making. The goal was to break down organizational silos by integrating multiple data domains into a unified environment. By doing so, it could support managers in making better decisions about how to allocate workspaces, assign equipment, and understand usage patterns across the organization. We followed a structured methodology grounded in system engineering. We began with stakeholder interviews to understand pain points and needs. We translated those into both functional and non-functional requirements, and then we used formal modeling tools like UML use case and sequence diagrams to visualize system behavior. The result was a high-level architecture supporting a modular development and adaptable to different organizational contexts. So stakeholder input was crucial in shaping our system. Organizational unit managers needed tools to allocate space efficiently, while technical employees from facility management, human resources, and ICT teams needed interface to input and manage data about buildings, people, and equipment. Among the main requirements were real-time visualization, floor plans, and the ability to filter or search using complex queries. Ultimately, we extracted 35 functional and 15 non-functional requirements, covering everything from login procedures to GDPR compliance and user interface design. To formalize system behavior, we defined key use cases like logging in, loading domain-specific data, visualizing occupancy, and allocating employees. Each user type interacts with the system in a specific way dependent on their role. So, for example, if we look at the image on the right, facility management technical employees, for example, they can input spatial and furniture asset data. So they input this data to the system, which then sends the data to the GraphDB, and this updates the visualization and reports. While if we look at the sequence diagram in the middle, we have organizational unit managers who use those data to make space allocation decision. And these diagrams, they were useful to ensure clarity in system interaction and support a modular development approach. The system architecture proposed a digital twin environment composed of 3 layers: the data layer on one side, the visualization layer on the other, embedding user interfaces, and the application layer in the middle, which integrates semantics and queryability tools. The system incorporates access control and authentication, and it uses ontology to ensure semantic alignment. It is event-driven, meaning it is designed to react to user interaction or data updates. The core idea was to enable real-time contextual insights from heterogeneous data sources, including code-based and AI-based automated transformation pipelines to a centralized knowledge graph, to finally support informed and efficient decision-making across organizational units. So we tested the system using a real-world case study at the University of Turin, specifically in a historic administrative building. Data sources include building topology, employee records, and ICT assets and furniture inventories. Each data point stored in RDF knowledge graph is linked via custom workplace management ontology, which aligns and extends standard ontologies like bot, real estate core, friend of a friend, the organization ontology, or schema.org. And here is an example of the nodes and relationship of the resulting graph containing anonymized data about occupants and allocation. So a web app then has been built using a Django framework and integrating a graph database with semantic data via its endpoint. In this case, it was GraphDB. The user interface was designed to present different views based on the user role, allowing managers to make allocation and technical employees to update asset records. Both retrieval and insertion of data between the visual interface and the backend graph are managed through Python function, which embeds Sparkle queries of varying complexity. As an outcome, the system provided a centralized intuitive platform for managing office space allocation. It reduces the time and complexity of workspace planning, supporting collaboration between organizational units, and it improves data accuracy. Most importantly, it promotes a shift from reactive to proactive decision-making with scalability to other domains like energy use or inventory lifecycle management. Early results showed better usability and coordination, promoting more data-driven workplace strategies. The study faced both technical and organizational challenges. Integrating diverse data sources, ensuring semantic consistency, and handling privacy and security were key technical concerns. While from an organizational standpoint, instead, change-resistant and personal knowledge seems to hinder adoption. Future work might not only include refining the user interface, but also developing phased implementation strategies, as well as integrating predictive algorithms regarding spatial occupancy and energy efficiency optimization. In fact, this study envisions a system that not only informs, but eventually recommends optimal decisions. To conclude, the system offers a practical, scalable solution to modern workplace management challenges. By combining digital twins, semantic web technologies, and system engineering principles, we created a system that bridges data silos and improves organizational decision-making. The case study demonstrated the feasibility of our proposition, and we believe that the model can be adapted to various large institutions. So thank you for your attention, and I look forward to your questions.